As informações que estão aqui estão todas abertas, então.
Tá certo, beleza. So we're gonna move to English. So it's a pleasure to welcome Professor Breno Marques. Professor Breno Marques did his bachelor's, his master's, and PhD in 2004, 2008, and 2009. Well, he got them in 2007, 2009, 2013 at Universidade Federal de Minas Gerais. And then he did a postdoc at UFMG, 2013. From 2013 to 2015, he was at Stockholm University in Sweden. In 2015, he was at USP for a postdoc. And since 2018, he is at UFABC. And today he's going to talk to us about photonic chips to implement quantum information protocols. Professor Marques, it's a pleasure to have you here. Thank you very much for accepting the invitation. And the microphone is yours.
Yeah, thank you very much for the invitation. It's a pleasure to be more or less in Minas Gerais again. And this, just to contextualize, this is a project that I got funds from FAPESP this year. So we are just in the beginning of this project. So what I will present here, it's more like what we want to do during the next 5 years. So, and thank you very much again that I can talk about it. So we have, just to make sure, just to say that we are part of the INCT de Informação of Quantum Information, and some of the equipment that we use in this project, it's found by them too. So, and this is part of the quantum information group in UFABC. So this is I don't know who will be part of this colloquium. So I did everything very from the beginning, and I would like to introduce some concepts that it's part of this project and talk about what we want to do. So first of all, let's talk our target, that it's quantum information. So the quantum information, we can say that it's the studies of to implement informational tasks in a way that only quantum system can make. So we use these exclusively quantum mechanics effects to improve something. This can be security, it can be velocity, speed of a task, or sometimes maybe a task that cannot be done by a classical computer, but can be done by a quantum computer that use these effects. So we are talking about these things here. And when we talk about in a computer, in a classical computer, we don't think about platform because it's a well-established electronic devices that make most of the computational information. So a PC, a phone, etc. And the communication needs more or less, most of the time it's well established that it's from light, like waveguides, fiber waveguides, and Wi-Fi and 5G, etc. And in quantum information, we don't have this now. So this is not something that it's already established. So we have a few components that can be used to implement quantum information protocols. So we have photons in free space, photon in waveguides, trap ion, superconducting circuits, nuclear magnetic resonance are just few examples that we can use to make quantum information, quantum computation, etc. Implement this. So, and depend on the task that we want. Sometimes we want to use one or another, and different from the classical computer. Most of the time, this communication between them are not possible right now. And to establish the first, like the base of information, the computational system, we call this as a bit for the classical computation. We call this a quantum bit for quantum computation. So we use this nomenclature. The protocols of quantum information that you have heard about it in a sense, maybe it's quantum cryptography, quantum teleportation, and quantum games, and simulation of complex systems. So we want to use the quantum systems to make these tasks. And the simulation of complex system in special, it's the test to use quantum systems that you can control to simulate systems that are hard to manipulate or analyze, that these have quantum properties. So, and during this process of find the best platforms and the protocols that we want to use, we use the same implementations and similar theory to test the fundamental part of the quantum mechanics. So quantum correlations, how we can use these, realism, non-locality, and contextuality. All of these, it's part of this quantum information area of research. Given that we use this fundamental test most of the time as a figure of merit for our protocols of quantum information. However, we don't need to have this basic system as a two-level system, a qubit. We can expand this for a qubit, a D-level system, D-level quantum system. So this can have some interesting implementations and that we can use, because most of the time when we are talking about a qubit, we suppress some degrees of freedom of the quantum system that we use to encode our information. In this sense, we are losing possibilities to use this in a better way. So most of the time so it's interesting that we can use more degrees of freedom, or degrees of freedom that it's not dichotomic. And we will give some examples in the following. So, theoretically, it's already shown this type of system can be more noise resistant. There are some tasks that can only be done by a qubit. They, as I told you, they can encode more information in a single system. Most of the time, it's hard to generate these systems or to produce these systems. And if you can have more information in a single system, it might be something interesting. They have some exclusively quantum information protocols, and when we see, like, if you want to expand or quantum dimension, so the information code in a system, we can put more qubits together. However, even in this state-of-the-art quantum computation, like the superconducting quantum computers of Google and IBM, the operations that have more noise are the ones that communicate, that make the communication between two qubits. So when you have one single qubit, you don't need this non-local operation. So this can be something useful in the future. Okay, and we have few examples in the literature that if we use this type of, like, 3 qubits, 4 qubits, it not be possible to make the experimental implementation, but when you use like a dimension d equals 8 or equals 16, you can. Okay. In this and what about our project? We have a source of spontaneous parametric convention of entangled qubits that use polarization. So this is one part of our project. And the other, it's to use longitudinal momenta as a degree of freedom to encode information. And how, and I'll explain this in the form. Okay. So we are talking about here, so we have the qubits or qubits. Now we have to choose a platform. And to choose the platform, we have to have three things that we have to have high control of this. The first thing is the source. We have to have the generation of this quantum system in an interesting way, or we have this can be a generation of photons, for example, in a way that we can generate photon after photon in the same state, operating in the same state, or we have the superconducting, that all the qubits, it's more or less the same, and we can manipulate them in a way that we can prepare the states in a good way, in a high fidelity. The second step is the operations. So we have to manipulate this system. So if a system it's hard to integrate with other systems, it might be difficult. So we have to have them well preserved, so less noise, but we can manipulate. This is a case of some like a photon that we can to have operations that if we want to interfere two photons at the same time. So it's a little bit hard to have this operation. So it might be difficult to manipulate them like this. So these operations also need to be a high fidelity compared to the theoretical review. And we have to detect them. So we have to have detectors that they have high fidelity, they are compact, and if possible, a low cost maintenance. One thing that we can say about this detection is to use infrared in telecom band spectra. So in this area, when we are talking about single photons, most of the detectors are superconducting detectors. So to maintain these detectors, we have to have helium, liquid helium, to have the superconducting regime of the detector, and this might be costly. So in this, thinking about this, we are planning to work in the visible and near visible photons, so spectra, because we can use semiconductor detectors that it's with a high efficiency, and we can have them. So a photonic chip in this spectra, we have all these three possibilities, and I will talk to you in this presentation about the source and the operation. So, first thing, what is a photonic chip? A photonic chip is a device that we can use to manipulate the light inside. And this photonic chip, in our case, it's based in silicon. So we use the silicon nitride as our waveguide, as shown here, and the cladding, the external part, as SiO2. And the manipulation of the operations most of the time are based on the heaters. There are other options that start to be available in using electro-optics, but that it's faster, but most of the groups use heaters to control. So we have a heater here, and depending on the temperature, you use the reflex index of the waveguide, and this changes the phase of or a path. So here we have this. The interesting part of the photonic chips is that we can have a full table of interferometers in the free space in a single device. Just to make in all the operations, the source, everything in one. So this is something interesting for if we think about scalability of this of the photonic as a part of the quantum computation area. Here we have a picture of the photonic chips. This is when I was in USP in my PhD. Here it's a 10 cents Brazilian reais coin. And here you see this black part here. It's the photonic chip. But it's not only one, it's 20 photonic chips. This is just the source, but see that the size of these devices are quite impressive. The miniaturization of the setup. Okay, and we are talking about, so we have the photonic chips. First, I will talk about the encoding, how we encode information, what degree of freedom we use to encode our information in this device. Okay, most of the time we are talking about the regime of single photon. So we have photon by photon. So our system is a photon. So we use a degree of freedom of this single photon. And we have path. So the most common, the two most common are the path encoding, where the number of path in your photonic chip determine the dimension of our system. So this is the path encoding. So here it's an example of a qubit source. So the red, so there are entangled qubits. The red one here, it's one qubit, and the other it's his twin. It's twin. And here we have the frequency encoding. So instead of using the path to distinguish to encode information, we use different frequencies, like in a comb, a frequency comb. Okay, so this is the two types of most common examples. However, we can discuss if the frequency coding it's intrinsically a photonic chip experiment, given that we use controllers, EOMs, to outside the photonic chip to control this comb. Just the source, it's in the chip. So when you're talking about a single device to make all-in-one quantum information protocol, frequency encoding, it's not it's not a possibility. So we have just the path encoding. Okay, so we want in your project all-in-one device. So we want the source, we want the operations, and in the future we want the detections in the same device. So in this case, as I told you, the path encoding it's the one that we want to aim. And we have the manipulation of this path encoding, especially for qubits. For a qubit, it's just a simple interferometer, like a Mach-Zehnder interferometer shown here. So we have the two encoding path, 0 and 1, and we have a Mach-Zehnder interferometer that we can control with a heater this phase difference between the path inside the Mach-Zehnder interferometer, and we have the output. So with 3 phase controls, we can have all operations for a qubit. For a qubit, a D-level system, we can have these multiple 2 Mach-Zehnder interferometers, such as this one. As you can see here, we have these multi-port, Mach-Zehnder interferometers all together. Let me see here. No, I don't have this. I don't have a picture, but we have multiple of these Mach-Zehnder interferometers together to combine 2 by 2 all the path together. So you have, if you want to have a generic, a universal gate, so we have to have a generic unitary transformation. And to have this, using this Mach-Zehnder device, we have to have them all together, like many of them. So to implement the operations, we have other options. So this is the main these combinations of two Mach-Zehnder many Mach-Zehnder interferometer are the main state of the art nowadays. So the groups that implement quantum information protocols in photonic chips using path encoding, most of them use these cascade Mach-Zehnder interferometers. However, there are other options that we are interested in. And this is the multi-beam splitter interferometer. So it's not possible to have in a free space a single device that combine and split many paths. Like you have a beam splitter or a cube beam splitter, and you have just two entrances, two inputs, and two outputs. However, in fibers and waveguides, especially in this case, we have the possibility to have an interference of all paths together. Okay, like this one. So we have this, instead of combine 2 by 2, we combine all paths together at the same time. So these have some interesting properties because we can have a unitary that combine all paths together. We lose some mobility, some universality of this. However, we don't need to have many operations to have access to implement many quantum information protocols. If we choose correctly this multi-port beam splitter, we can have a unitary transformation that can be used for many quantum information protocols. And this is what we want. We have the phase shifters as input, we have the phase shifts in the output, and a single, not many, a single beam splitter. It's a multi-port beam splitter, but it's a single one. So this so if you are thinking about a photonic chip that it's a very compact setup, we are compacting even further using this multi-port beam splitter. Okay, so and it's simpler. It's a simpler photonic chip, so that we can have. So this is our results that we have now. It's part of the master studies of the Marques Cordeiro, and this is the first results that we have for as the simulation. So right now we are simulating our photonic chips to choose the the design that we want to implement. And here it's a simple, because it's a simulation, it's not like this that we have just the path alone and we combine them and then we split them again. We are just thinking about the combination of these paths, and we have to characterize them. So we simulate this multi-port beam splitter. Here it's a dimension 3, this is a dimension 4, and this blue, yellow that we see, it's the electric field of the source. The interesting part here, we are talking about linear optics. So if we use a high intensity or a classical light source or a photon, the operations would be the same. So we can use this in our favor. Here we have three inputs and three outputs. And we characterize our multi-port beam splitter choosing we have two possibilities. One is to find the amplitudes of each path here, that it's this matrix, P4 matrix, P5 matrix, P6 matrix. So we have here the amplitude, or we can choose to characterize as eigenmodes. So here we have this difference. However, when you split the path, both results are similar. But because here the eigenmodes of the propagation of the light here, they have a superposition. So because you have evanescent light that it's the splitting of one path in two, and these also make the eigenmode larger than the waveguide. So they are more or less in the same space. So that's why the difference. But we can see here that we can have the amplitude for a single input, and we have the output. Combine this with the information of the phase, and combine the source in each one of the inputs and the information of the phase, we can reconstruct the unitary transformation that we have in this multi-port beam splitter. And this is the master aim, the master thesis of the Marques Cordeiro, one of our students. Here we show for dimension 3. Here we have for dimension 4. You can see that when we have more path, we have to have a longer length to have the integration, the combination of all paths. So this is something that we are interested to see how this length changes with the dimension, and how this amplitude combination of the output changes when we change the gap. Okay. Most of these results are we use as base some works from USP that a group that we are collaborating. with this in this area. Okay, so we have the path. We choose the path as encoding. We know how to operate this path. Now we have to generate our system inside the photonic chip. And this, so we are talking about the source. Here we are talking how we generate these photons in your photonic chip. We use 4-wave mix. To have a single photon, we use spontaneous 4-wave mixing. So what we have a pump in omega 0, and given no linearities of third order of our system of waveguide, in this case the silicon nitride have these no linearities, it's already known. We have the generation of photons, the twin photons in omega 1 and omega 2. Okay? This happens when we have phase matching. So when we have in a simple way, we have the conservation of momentum of the light generated respected. So we have to have this delta K equals 0. So here we have the key, and here the phase matching. So we have generation just when we have here equals 0. In special, in our range that we want to use, the wavelength that we want to use, that it's visible and near infrared, we don't have the possibility to have this phase matching for the fundamental mode of the waveguide. So like a simple propagation in the waveguide. This, it's because we have to have anomalous dispersion. That it's when you see, so most of you might know that when you increase the frequency, more the refractive index, bigger is the refractive index. So this is our normal dispersion. When you have this the opposite way, we have anomalous dispersion. And we must have this to have the 4-wave mixing. In this case, as you can see here in this graph, here it's beta 2, so it's the derivative of the velocity group. So here, if here it's negative, we have anomalous dispersion. So as you can see here in this graph, for all modes, fundamental modes, the 0 represents the fundamental mode for TE or TM. This is polarization, more or less a polarization, horizontal and vertical polarization in the waveguide. In a simple way to explain this, see that we have anomalous dispersion above 900 nanometers. So in the range that we want to work, that it's around 800 nanometers, that it's here, we don't have anomalous dispersion. So the T0, the fundamental mode, it's not possible to use as a source. However, we can change the mode inside the photonic chip for a higher mode. For example, the first mode, that it's the one, this one, that it's 2 intensities with phase difference of pi. And as you can see here, we have anomalous dispersion in the region that we want to work. So this is a step that we want to make, and it's there is a paper here from USP that shows these results, and we base all this. It's from this paper. These results. It's not ours, but we base on this to build our source of spontaneous for wave mixing to produce our photons. Okay, so we have the source, we have the manipulation. How we can have all-in-one quantum all-in-one quantum information protocol implementation. This is more or less a design of a chip that we want to build, to fabricate, and we have here the spontaneous four-wave mixing happening in a ring resonator. This ring resonator is just to amplify the non-linearity, so we have more intensity, we can generate more with more frequency. We have a demultiplexer because the photons H1 and H2 must have different frequencies, so we can have a demultiplexer. So just one of the photons here, the one that it's represented as this blue arrow, resonates with this. Resonates with this ring. So just this photon couples with the ring, and we have then the output here, and the other comes here. So here it's a heralded source, so we use one of these photons to announce the other based on the coincidence of the in the detectors. So we have the preparation. This is a multiple Mach-Zehnder interferometer here in this case, and we have a generic quantum unitary transformation. Here we combine using these all three paths, and here we detect in coincidence. So we just detect the coincidence. So we have to have two photons to have the coincidence. So they must have the source. They come from the source, not from other thing. So this is an example. We can change the source for multiple source as shown here. See that we have multiple. Here it's a ring. It's not a ring. It's a single path, so that it's in circular and come back. However, they are multiple, given and using multiple spontaneous four-wave mixing source, we can have entanglement between paths. So this is what we want to make also. Okay. So how will be our experiment? We have the pump that will give the energy needed to generate the photons, or as a pump laser, or we have a source of twin photons using spontaneous parametric conversion. You can use these photons as our system together directly in our photonic chip. We have our photonic chips, so based on what we want, we can switch between these two sources. So if we want to make a source like a ring resonator, we use the pump. But if you have a single photonic chip that have only the unitary transformations, we can use the twin photon source to implement the operations. And the interesting part that if you have two photonic chips, we can have both operations made by the photonic chip. So this is quite interesting. And we have the detection. As I told you, the detection won't be made inside the photonic chips. They will be made outside. We use like photo detectors. We can use CCD cameras. Or single photon detector, depend on what we want to analyze. For example, if we want to analyze the noise of like the fluctuations of this system, we can use photon detectors using homodynamic detection. If you want to see how this is split as a single interest, we can use a CCD camera like a Young interferometer, like a split. So we propagate as a split, and we see in a CCD camera. And when we want to make the protocols itself, when we are talking about single photon, photon by photon, we use the coincidence unit in a single photon detector. Okay. How time is it? So I will talk here about the first protocols that we want to implement, because as you see that we have the preparation and we have the operations that we have to make in the system, but there is a type of protocol called prepare measure protocols that englobes many of the protocols that it made in photonic chips and in light in the photonic systems. So it's the prepare measure protocols. What is this type of protocol? We have two parties, Alice and Bob, using the nomenclature common in quantum information. So they have a task. I don't know which task it is, doesn't matter, but Alice has input X, Bob has input Y. They need to collaborate to have a task done. And most of the time, what we want is that the input information of Alice will be encoded in a quantum system. Here, psi X or rho X. Okay? This quantum system will be sent. Alice sends this to Bob, that will measure this quantum system, that the input based on the input Y that he got, and they will have the output B. Okay, we will have, depend on the results of B, if the task is successful or not. Okay, and what we want most of the time is that the average success of probability in the quantum scenario, it's better than the classical scenario. So the best way to make this task in a classical scenario. Okay, so we represent most of the time this average probability of success in this cache. So because of the way that because this is used in quantum game game theory, so we use cache here too, and the quantum case need to be better than the classical case. And many of the protocols based on this simple example, okay, this simple task, this prepare measure protocol, this prepare measure, we have many famous quantum information protocols like quantum cryptography. It's a type. There are many quantum cryptography protocols that it's a prepare measure type, like BBH4, that it's considered the first quantum information protocol. The quantum random generator, most of the time, it's a prepare measure protocol. Remember that a classical random number generator, they will have a bias. So, and here we won't in quantum because of the randomicity, the intrinsic randomicity of the classical measurement, and the random access code, that it's the main interesting here because many quantum information protocols can be put together, can be written, can be analyzed as a random access code. Okay, just to give you this example, how a prepare measurement protocol works. Here it's the random access code that the input information of Alice, that it's a classical, it's a word, a random word that it's written with any letters, any entries in an alphabet of dimension d. Okay, and the task is Bob needs to find what is the wife letter of the word that Alice have. However, we have a restriction of information that Alice can send to Bob. Okay, so this message has to be smaller than the information need to written all the word of Alice, and we have the average probability of success given by this. So, given X, the letter, the word, and Y, which position of the letter that Bob wants, I want to have an output of Bob that it's B equals XY. If this is true, we have a success. However, otherwise, we fail. And this is shown that we can use quantum mechanics to improve, to have a better, a higher average success probability in the quantum scenario compared to the classical scenario. Okay, and given that seems simple, this protocol, and it is. However, the applications are huge. We have many applications in this, and that's why we aim to implement this random access code as our first quantum information protocol in our photonic chips. Okay, so what? So I present here for you that the photonic chips, it's a viable platform to implement quantum communication, quantum information protocols, because we can have the source, the state manipulation, and there are some works also showing that we can have the detection in the same photonic chip. This is not addressed here, but it's something that we want to have in the future. Okay. As I told you in the beginning, this project started this year. So this is very preliminary results. And we expected in the next 5 years we have the photonic chip running fully in our lab. And as I showed you, we start with the simulations because we want to have new designs that it's not used for other in other groups. So this is something that we have to start it from the beginning. And we are studying the spontaneous full-wave mixing source, the unitary operations through multiple beam splitter. We also want to have the polarization control in photonic chips. This is quite hard to have to use our entanglement source that we have in our lab to communicate with them. So this is something that we am, and we have also which type of quantum information protocol are interesting to be implemented in this setup that, or it's hard to make in free space or in other platform. Okay. I call you to work with us, especially to collaborate with us, and we have a master and a PhD scholarship from FAPESP that is integrated, that it's part of these funds that we got from FAPESP, and we also have the UFABC physics graduate program that you can find in this website, that you can see what we work and other projects that are the other professors of our group in quantum information and other groups also work. Okay, and we are founded by FAPESP, Institute of Quantum Information, in Cap Sprint, that we have collaboration with groups outside Brazil too. Okay. Now, these are our 4 students that work. Eduardo, Marques Cordeiro, the results of the simulations that I present for you were made by Marques Cordeiro, Fabrício that works with our fault, and Giovanni Pinheiro that it's working with quantum information protocols in theory. Thank you.
Thank you, Breno, for this nice talk. We are open to questions. We have some quantum information specialists in the audience.
Okay.
Johnny is here. Vilas Boas. So I have a question. I am from a completely different area, a strongly correlated theory. Oh, I see we have, before I ask anything, Jader wants to ask a question.
Okay. Hello, Jader.
Jader, go ahead, please.
I think you are in the just listening.
Oh, yeah, you need to.
He entered.
Yeah, I think you have to get out and in again, and then allow the microphone.
Yeah.
So why? Oh, otherwise you can write your question if you want. Let's see.
Yeah, it's other things here.
So why would Jader is doing that? Let me ask my question. As I said, I'm from strongly correlated theory, Kondo, Q-plates, this kind of stuff. So I was intrigued by the qubit thing because we are so used to the qubit idea.
Yes.
And I thought most of the implementations were done through qubits. Do you know? Would you know of an example of a qubit in an atomic system, for example, where you can do maybe NMR, a high speed?
Yeah. We have some examples in NMR, some examples in ion trap. In ion trap, use more than 2 levels, but most of the time you have to worry about cross other levels that you have to access. So it's hard to have 2-level system. It's quite simple to have in atomic in ion trap. However, when you have more, it's hard to choose. I just want 3. I just want 4. So you have a optic and a communication that it might be difficult to control. So if you increase your system, but it's too much difficult to integrate to have the Hilbert space larger, it might be simpler to have them more qubits. In the case of the ions, it's simpler to have more ions. So you have like a full trap with many ions to have. In the case of the NMR, you have some examples with spin 1 and spin 3/2 that you can use, but most of the time, given that in the case of the ion traps, in the NMR, the communication, these operations that combine, that it's between 2 qubits, it's a high fidelity. They have a high fidelity. It might be simpler to have many qubits instead of a qubit. In the case of the light, in the photon, that we have this, because it's really hard to have interference between 2 photons. The only operations that we know that combine 2 photons is the Hong-Mondel interferometer, that it's that bunching that it's based in bunching effect, and no linearity effects, that most of the time they have low intensity, so it's hard to make them. So when you are talking about photonic chips, it's better to have them increase in degree of freedom instead of the many systems.
So that's the best system for qubits.
For qubits, yes, because of this. To increase the dimension of your system, to increase the encoding possibilities, you have this seems for me as the best scenario. Independently of the degree of freedom, you have translational paths that the works in the UFMG, and the angular momenta that the Universidade Fluminense and Santa Catarina also work with. So we have these possibilities too. Just talking about our Brazilian groups.
I understand. It's good to know that they exist.
Yes.
Yeah. So, Jader, you can ask your question.
Hello, Breno. Can you hear me?
Yeah.
Well, first, I'd like to thank you for accepting the invitation. It was a nice talk. Thanks. And I have a simple question. Is that possible to generate this path encoding using diffraction grades inside a sheet photonics, a photonic sheet? Or is not possible? No one have generated yet?
No, no, I haven't seen someone generate that. There is the UFRJ group that using Hammond, high order Hammond, that you have more than one photon generating by Hammond in a crystal, but it's a free space source. In the techniques that it's usually used to implement to fabricate these photonic chips, we don't have this possibility to generate like that. I think. Okay.
I can't see any possibility too, because how to generate a grade inside the waveguide.
One thing that you can have that it's I think it's the closer possible. It's this frequency encoding, because they are collinear, and the encoding it's in different frequencies. So, and you have the EOM to communicate between these. So you change the frequency using the EOM. And the detection are made, the projection are made by the multiplexer. So this is something that there are a few groups in the world that use this source, and it's quite interesting because what restrict, because you have a long you can generate a really long cone with many peaks, so you have a dimension, a higher dimension. You have 100, 1,000 maybe you can have. The problem is if your EUM, your modulator, can combine all possible frequencies, and so it's not a photonic chip problem, it's the EUM problem. So the restriction that we have in this scenario. Okay.
There is any group here in Brazil doing this frequency encoding? The guys from USP?
No. Right now, if I'm not wrong, I'm sorry if I forget someone, but working with photonic chip, we have groups in Unicamp, in USP, and now after this found in UFBC. So I don't know. There are I know that they are interesting from Sebastian in UFMG. They have some theory paper that they analyze these qubits in photonic chips, and Daniel Felinto in UFPE also show some interest in this, but I don't remember other groups that work with photonic chips.
Okay, thank you, Breno.
Oh, welcome.
Any more questions, anyone? See that Vilas Boas is there.
Hello.
Hello.
Hello. Vilas Boas, yes. Go ahead.
I'm trying to...
There you are. There you are.
Hello, José Maria.
Hello. Thanks for the nice talk. Might be a stupid question, but how do you cope the light with the photonic environment, with the chip?
Okay. Here it's an example. Okay, this is a taper that it's more or less a fiber that we like make a taper like a wedge that will be coupled in a single waveguide inside the photonic chip. Just after we will be split them.
But don't you have a scattering of light when you try to couple with such
yes.
small device?
Yes, we have. This couple can be quite hard and difficult to align as an experimentalist. I know how hard this can be. Yes, we have losses with this, but there are this type of coupling. There are other with evanescence waveguide that instead of putting like this, we put like this. So the fiber in your setup. So these make the coupling as evanescence really similar to the beam splitter inside the photonic chip. We can also have that it's the most efficient way that we got, that it's using objectives. So this is also possible. Okay, but yeah, there are losses, but most of the time we are coupling classical light. So
okay, I thought you were connecting single photo sources to these things.
Yes, if we want to make this, and this will make noise. This will have a lot of noise losses. This is something that we are trying to see what is the best way to make that. But when you are coupling classical light, doesn't matter. It's just to put more power there.
Okay. Thank you.
Welcome. And it's not a stupid question. So
any more questions, anyone? So if not, let's thank the speaker again. Thank you very much, Breno, for this nice talk.
Thank you.
I will be sending you an email asking for the slides. If you don't mind, we're gonna put the video in our YouTube channel in the in our program webpage. So if you have anyone who may be interested in couldn't be here today and is interested in seeing your talk, just let me know and I give you the link for the YouTube channel.
Okay, no problem.
Okay, thank you very much. And
thank you.
Okay, thank you. So have a nice day.
Bye bye. Have you too.
Bye bye.
Bye bye.
Thank you.
Thank you, everyone.